Good afternoon. It's great to be back in Berlin, one of my favorite cities. I'm going to talk to you today about test-driven data analysis, which is a topic I've been talking about for a little while now. This is my first sort of full PyData presentation on it, so I'm going to spend the first half reviewing the fundamentals of what it's about and then talk a bit about some of the newer developments and where we're trying to go with it. And my goal today is really to convince you that if you do data analysis or data science or anything that involves data really, you should be doing test-driven data analysis. So the idea for this comes from software development, where some of you will be familiar with the idea of test-driven development. I think it's certainly the most important development in software engineering practice in the 30 years I've been doing it. It's the sort of common heart of all the agile methodologies. And the idea with test-driven development is that if you're going to write some code, suppose you're going to implement a division function, before you implement a single line of that division function, you first write one or more tests that specify something about what a correct answer would be. So you say, you know, when you divide 6 by 3, it should give you 2, or something like that. And there are frameworks that allow you to run that test without having written a single line of code, and the test will typically fail, in fact, typically generate an error at that point. And then the idea is that you write code to make the tests pass. Possibly you correct the test if you had mistakes in your test as well. And you only write code when there are failing tests. So if you want to extend the functionality, you write some more tests to specify that new functionality. If you get a bug, you first of all write a test that demonstrates what the correct answer would be, and then implement the code. And this turns out to be amazingly powerful. Not, in my view, so much because of the idea of writing the tests first, but because what this results in is that you have this big set of tests that you can run. And the idea is typically that you run these tests all the time, like quite literally having a continuous integration system that is running them in the background and reporting if they stop working. And this has various good consequences, but the bottom line is it makes code quality much better, particularly because if you have a lot of tests that specify what the code's supposed to be doing, it gives you freedom to rewrite that code without worrying that you're breaking it, whereas one of the big problems with legacy software typically is no one dares edit the code because they know that they'll just break it, and if there's not sufficiently good test coverage, that's difficult. Anyway, that's the motivation for test-driven data analysis. And so one of my good friends and colleagues, Patrick, said to me one day, you know, we should do test-driven data analysis as test-driven development. And we both instantly thought this was a great idea. The trouble was we had no idea what test-driven data analysis meant, so we spent the last few years trying to figure that out. And the trouble is, data analysis typically doesn't look as organized as that software development process I've drawn. I don't know about yours, maybe yours does look organized, but what mine normally looks like is something like this. You know, you sort of catch some data from someone. It typically doesn't have a data dictionary. It's typically very hard to understand what it means, and you spend ages trying to eyeball the data, trying to figure out what on earth's going on, sanity checking it. You start swearing at people because clearly it was a maniac who put the data together. You've got duplicate values, the join keys don't work. There are missing values, there are crazy encodings, there are numbers where there should be strings and strings where there should be numbers and all this kind of stuff. And it takes ages to get to the point where you have any confidence in what you're doing at all. So how do you apply, you know, something like this to the process that we're all familiar with? So the goal is to take this idea from test-driven development of testing for software correctness and having lots of tests and testing all the time for software correctness, with the same idea for data analysis, testing that your data analysis is correct, but adding the extra things that make data analysis more complex. That is, we have to worry about the meaningfulness of the analysis as well as the correctness of the analysis. We have to worry about the correctness and validity of the input data. And we have to worry about correctness of interpretation. You know, it's not really good enough for us to say, well, we produced the correct result. It's not our fault if you thought 99% meant it was 99% safe to go, whereas in fact it meant it was 99% you're going to die if you go. It kind of really is our problem. Or at least I think it should be our problem. So When I look at, so we talk about analytical processes, and really by an analytical process, we mean absolutely anything that starts with data and produces some kind of a result, whether that result is itself a data set or a report or a single number or an insight or whatever. But typically working with some reasonable volume of data, not just like 3 numbers. And typically these days we find that there are 2 phases to the thing. There's a development phase when you try and figure out what the analysis is going to be. And that starts with choosing the approach. So this is when you are doing all your eyeballing and figuring out what algorithms you're going to use and what packages you're going to use and all the rest of it. And one of the things that can go wrong at that stage is that we can fail to understand the data, or we can fail to understand the problem domain, or we can misunderstand the applicability of algorithms or methods or whatever. And if we do that, then obviously we fail and we produce, in general, an invalid analysis. And we call those errors of interpretation. It's something about our interpretation of the data or the problem that's gone wrong. If we don't do that, then we have to do some kind of implementation. And obviously here, a lot of that would be in Python. But I'm really counting anything as implementation, even if it's just doing something in Excel or using a package. There's still the process of taking your data and making whatever software you're using perform the analysis that you want. And if something goes wrong there, we call those errors of implementation. But of course, they're just bugs. They're the familiar, easy ones. And we only get the answer right, if we don't make either of those kinds of mistakes during that development phase. And once upon a time, I think that's what a lot of data analysis looked like. But certainly what we find is that these days, there's almost always an operational phase as well, where we have to take that, whatever that analytical process we've developed is, and put it into production in some form, either a self-learning system or a scoring system or a reporting system or whatever it happens to be. And that tends to be true even if it was just a kind of someone asks you to do something and it'll be a one-off analysis. Almost always they come back 2 weeks later and say, that thing you did, could you just do it again on the updated data? Or indeed, it turns out the input data was wrong. Could you do it on the correct data? And so during that operational phase, we get a whole load of extra opportunities for things to go wrong, because now we have to run that analytical process that we've developed. And there's the opportunity to use the software incorrectly, even if it's something as trivial as, we get the parameters in the wrong order, or we forget what file it is, or we think we're putting in one file and we're actually feeding in another file or something. We call those errors of process. There can also be, perhaps the most worrying one, there can be a mismatch between the data that we use in operation and the data that we used in development. We call those errors of applicability. So it's not a bug, it's not a fault that when we develop our software, we do it in the context of one or more specific data sets. We have to do that, otherwise we're always trying to solve a completely general problem, and that doesn't work. But it is important that when we deploy that thing, that analytical process, that we deploy it with broadly comparable data that would have led us in the same direction if we'd used it for development. And if that goes wrong, that's very serious. And the final thing is when we get the output, we still have to interpret the results. And so there's another opportunity for an error of interpretation there. And it's only if we get through all those phases that we actually get the right result in general. And when I say the right result, I'm not talking about whether the result's off by like 0.1% or something. I'm talking about even the sign being wrong, or even completely misunderstanding it, as I say, taking off when the system was telling you it's not safe to take off, lending to the wrong people, whatever it happens to be. And then, of course, because it's an operational process, we get to go around that loop many times and make the last 3 mistakes as often as we want. So if you take this at all seriously, if your processes look, and they don't look exactly like this, but if you buy that this is something like what modern data analysis looks like, it's quite sobering if you put some numbers on. Now, I'm extremely optimistic and extremely good at this stuff, I'm going to claim. So I've put very, very optimistic numbers, like I'm going to say there's only a 20% chance that I'm going to misunderstand the data or the problem. And there's only a 30% chance I'm going to write important bugs when I implement the process. And there's only a 10% chance I'm going to forget how to use the software when I run it. And there's only a 20% chance that I'm going to throw completely the wrong kind of data at it. And there's only a 10% chance that I'm going to misunderstand the output, which all seem like pretty optimistic numbers. Now, if you're all much better at data analysis than me, put your 90, your 95, your 99% in. But with these, I think, quite optimistic numbers, your chances of getting sort of broadly the right answer the first time through are only 36%. about 1 in 3. And I'm not for a moment claiming that's a real number. These are made-up numbers. But they actually feel broadly congruent with what we find. It usually takes a number of runs through before it starts to work. And every time you go through, there's at least the potential for that to degrade again, though there's also the potential for it to get better if you find problems and notice them and fix them during the process. So this is the picture we're working with. And test-driven development as not just an abstract thing, but as a real thing, as a software library you can use and as a set of things we're developing, has 2 major components at the moment. The idea of reference tests and the idea of automatic constraint discovery and verification. And I'll talk you through what those mean. So I'm going to talk about these in more detail, but very briefly, a reference test is, for those of you who know what they are, a bit like a system or integration test in test-driven development. In other words, it tests. Really, the way to think about a reference test is it's capturing what you did when you developed the process, including the data and the code, and checking that it still produces that same answer later, or a set of tests, a set of things that you did when you developed the code, and checking that they still work later. And we'll go through the details. And the second bit, the automatic constraint discovery and verification, is all about getting the system to characterize data that you're using at various stages for you in the form of executable constraints, and then checking those constraints against the data that you run later. These turn out to be quite powerful ideas, so we'll go through them in more detail. I should say there is an open source library on GitHub and PyPI, so you can just pip install it or git clone it if you want the source. It runs on Python 2 and 3. It runs on basically all the Linux and Unix and Windows platforms. It's MIT licensed, it's documented, and there are even reference sheets and stuff, so you're welcome to use this stuff now. We do have commercial software as well, and we tend to develop the ideas, and it's called Miro, and we tend to develop the ideas in the context of that, and then when we've figured out how they're really supposed to work, we tend to copy them into the open source TDDA library. So some of what I'm going to show you is not currently in this library, but it should all make its way into there. We're not deliberately holding anything back, we're just sort of not inflicting our half-baked stuff on you. So reference tests. Another connection here, which I didn't know about when we started doing it, is reproducible research, which I imagine some of you will be familiar with. Reproducible research is a movement within the academic community to get anyone who publishes, particularly scientific research, but any database research, really, to publish not only their paper, but their code and their data, so that other people can run it and learn from it and check it. And one of the important parts about that is encapsulating it. Not just dumping the data, but not the code to pre-process it into the form, but dumping everything that you need to be able to use that code. So it's not directly about the computer helping you be more likely to get your analysis right. It's about trusting other researchers to look at it and say, this thing here on line 20, that's nonsense, or this input is producing this output, and that doesn't make sense. But this idea of capturing, so when you develop your analytical process, you're going to do it in the context of some data, and you're going to convince yourself that the answers are right, or at least good enough to use, or at least good enough that you didn't abandon them. And so the idea is that you capture those things together. You either take all of your input data, or at least a sample of it, you take your code, you freeze it all, you put it together, and preferably wrap it up in a script so that you can just type, run or whatever, and the whole thing runs. And then you develop some kind of a difference procedure for checking whether the output's what you expect. So if it's just a number and it's supposed to be 42, you check that the answer's 42. If it's a great grid of numbers, you check that it's the right grid of numbers to whatever level of precision is appropriate. And what you might think is that if you do that, and you save the code, and you save the data, and you run it, and then you run it a week later, and you run it a month later, and you run it a year later, it's bound to work, because nothing's changed. How could it possibly not work? And the bad news is that actually most of the time it doesn't. And there can be myriad reasons for that. You upgraded your operating system. You upgraded your version of Pandas. The operating system upgraded the operating system. Your colleague upgraded the operating system. You installed a new version of a package. You made a tiny little test that couldn't possibly tweak to handle some extra case that couldn't possibly break anything, and yet your helpful colleague made a change to handle some case you hadn't thought about. And this is before you even move it onto a different operating system, a different computer, a different time zone. And even if none of those things are changing, your disk can get corrupted. Time changes. I mean, you paste data into Excel, and what comes out depends on the actual date on which you do it. It's, Hopefully your code doesn't do that, but these are the sorts of things that can cause this not just to work. So in the TDDA library, there is support for reference testing, and I'm going to rather foolishly try and show you that. And it's support for this same style of allowing you to run tests, even given the sorts of things that you need with data analysis, like maybe the data isn't really exactly the same, maybe you've pasted a date into there, maybe there are precision issues, maybe there are all sorts of things that might be slightly different about the data. Maybe you're using a graphing package and the actual, code the code that it generates for the graph is different, but the graph still looks the same, so it's semantically the same. There's lots of support for helping with that kind of thing. So I'll show you a small example of this. Where am I? So if you do have the library, you can, and I'm sorry if this is a bit small, I've made it as big as I can, reasonably. You can say TDDA examples, and it will copy a set of examples for you. And if you go into that, there is a little thing that generates a data frame. It's an incredibly simple function. It just generates a thing with half a dozen columns, 10 rows, mostly fixed fields, but one random number that obviously we don't want to test as part of our thing because it's a random number and it's not going to be the same from run to run. And there are pre-canned examples of tests. So there's a test that checks that you get the right data frame out. In fact, there are several tests of that. And if I use the unit test version and run it, those of you who've seen this sort of thing before will see it's just running its 5 tests and they're all passing because, well, examples are supposed to pass, right? But suppose we edit this code. If I can find my editor. That is the right one. So this very simple code, one of the things it does is it prints out that last number to 3 decimal places. So let's just change it so it only prints it out to 1 and assume that's what we now want. If we run that test again, then now we get failures because obviously we've changed the output. We're generating the data frame to a different precision. 3 tests are failing, which is a bit confusing. There's lots of output, which is a bit confusing. But one of the things it does is it gives you in here the command that you need to use to actually see what's changed, which is helpful, a diff command. I'm going to use opendiff, the graphical one. I suspect you can't read that. Yeah. OK, so you have to take my word for it that the stuff it's highlighting on the left that's different is the random numbers that are supposed to be different, and that's fine. And the stuff on the right is that column that's now only got 1 decimal place instead of 3 decimal places. And so as part of our diligent checking, yes, that really was the bug fix or change that we wanted to make, and this is now the correct answer, I'm going to, and assuming we did that with the other 2 tests that failed as well, I'm now going to assert this is now the correct answer. And what the library lets you do is if you now run the tests again with the exact same thing but add a minus capital W on the end, it will rewrite the answers that it uses as references to check against, saying, OK, someone's told me these are now the right answers, so I'm going to copy those. And if I now run the tests again without that minus W, they pass because obviously they're reflecting my change. So that was a bit fast. There's lots of documentation on all this stuff. Well, there's some documentation on all this stuff if you want to play about with it. But this turns out to be really powerful for spotting when things break that you didn't realize. I'm not going to go through the detail, but it's on the slides. So that's that. OK, constraint generation and verification. How am I doing? 20 minutes. Yeah, OK. So if we go back to our analytical process that I think every one of you agreed is exactly what analytical processes look like, one of the things we didn't really talk about was what happens when you feed bad data into this, either during the development or the operational phase. So if you feed bad data in during the development process and you don't recognize it, the chances are you're going to produce a bad process because you produce the right answers but from the wrong data, or answers you were happy with but from the wrong data. So that's not good at all. And if you do it during the operational phase, the chances are you'll be passing in data that you didn't really design your process to deal with, and therefore bad things will probably happen. So bad data is a problem wherever it occurs in the process. And the idea with this constraint stuff is that almost always we're dealing with, well, one very common example with our data analysis is to use data tables, a data frame or similar as input, or a set of data frames. It might be JSON or something like that. We're concentrating on tabular data at the moment. And there are many things that we know should be true about that data. And in principle, we could write all those things down. But the thing is, we're lazy, and we're human, so even if we did write it down, we'd screw it up because that's what we're like. So the big idea is to get the computer to do that work for us instead. So here are some examples of the sorts of things I'm thinking about. If you've got an age, it probably shouldn't be more than 150 if it's a human. And it should probably be an integer, or at least it should almost certainly be a number. And if you've got a customer ID and a master table, it probably shouldn't have duplicates. And if you've got a credit card number, it should probably have 16 digits, and so on and so forth. So there are things that ought to be true about fields and the values in individual fields. There are things that ought to be true about data sets. Maybe you have to have a particular field in a data set, even if it's allowed to have some fields that come and go. Maybe you've got constraints on the number of records. Maybe some fields ought to be tagged in a particular way. And there also might be relationships between your fields. Like if you've got a field called start date and another one called end date, it might be that the start dates are supposed to be before the end dates, or at least not after the end dates and stuff like that. So all of these are things we could write down, but we never do. So, and actually an example of this, which again I'll do live because I'm stupid. If I load up some sample data and show you it. So this is price. So Skyscanner, you probably know, it's an online flight travel service that it doesn't sell you flights. It's a meta search, so it has Expedia and Last Minute and all the airlines as partners. It just tries to show you the best price. So they're getting pricing data all over the time. They've got like 1,000 partners, and they're integrated with 1,000 partners, so they're getting data in all the time. And when you've got 1,000 integrations, they break from time to time, and you get bad data through. So here's an example of just some records that we get through. I've anonymized the sort of incriminating stuff, though I haven't changed any of the numbers. And eventually you get to ticket price, and so you see some ticket prices and card fees and card types and stuff like that. So let's just look at what happens when we use, this is Miro, and I'm going to generate the constraints in Miro, but you'd get almost exactly the same answer if you did it with the TDDA library in a pandas data frame, well, the same pandas data frame. Our disco command, which is just short for discover, it's the discover command, really. And so if you do that, it goes through and does a lot of fairly simple things and some slightly more complex things. So the first thing it says is, well, this request ID field, that's a string, so I'm going to turn that into a constraint that it must be a string field. And I notice that the lengths of all the strings in that field are 36, so I'm going to set the minimum allowed length as 36 and the maximum allowed length as 36. And sign is only for numeric values, and it notices that there are no nulls in there, so it's going to say nulls are not allowed in this field. And it doesn't say that duplicates aren't allowed, so that means that there must have been duplicates in that field, because if there had been no duplicates in that field, it would have said this field doesn't have duplicates. And that's an interesting example, actually. You might think the request ID ought to be unique, and the fact that it didn't, this is what I call the curious incident of the dog in the nighttime thing. When you look at a set of constraints that have been generated, you not only have to look at the ones that are generated, you have to look at the ones that haven't been generated as well to see whether actually they should have been generated, and that's telling you something about a problem with your data. So those things are all fairly straightforward, and it does the same sort of thing with numeric fields and so forth. The last two columns are slightly more interesting. The first one is values allowed. If it sees a string field that only has a small number of values, it will actually say, this looks categorical to me, and I'm going to say these are the only values that are allowed. And regular expressions we'll talk about in a minute. That's one of the new things. But it also generates regular expressions to characterize the fields that you've given it, which is definitely more sophisticated. So it writes these out. It writes them as a set of constraints. I actually didn't do it there, but I know I have one kicking around that's very similar to this. So what these look like is, so they're JSON files. And again, you get exactly the same thing out of our software and out of the open source library. So it has some metadata at the top, and then for each field it goes through and lists a set of constraints that it knows how to interpret. So here's the regular expression it's generated for the request ID, which is a UUID you might recognize. So, OK, so let's just see what happens if we, so this was done on a small sample of the data, like 15,000 records or something. I'm going to use a slightly bigger sample Still only 300,000 records, and I'm going to verify against that. And what verify does, it must have constraints on it. What I should have done is told it to verify against that particular set of constraints. So I'm surprised it's working. But anyway, yeah, OK, that's interesting, actually. But it's verifying against some set of constraints, probably more or less the same constraints. And what it's doing is it's just going through and testing each of the constraints against the fields and saying, does this pass or does this fail? And if not, giving you some information about how it fails and generating a whole load of data that you can use. So it's getting there. In a minute, we'll see what it didn't like. What it didn't like is the fact that I didn't actually verify against the right data set. Right, we'll try it once more, and then we'll move on. And you'll believe that it works really, because it does. Yeah, this looks better. This looks better. Let's just whip through the slides slightly. So while it's doing that, hopefully it's going to get through. So we've done that. Oh, and there's an example of what it should produce, and probably has just produced. It hasn't finished yet. Well, this wasn't how it was planned to happen. OK, so while it's just finishing off, an important point to make is this is not just for input data, right? So when you're doing your data analysis, you will probably use multiple data sets for input. You'll probably transform them in various ways, and you'll probably go through a whole series of transformations before you finally present the thing to whatever your analytical application is doing, your model or whatever it happens to be. And then maybe you'll do some more transformations on the outputs before actually dumping them into a report. And every time you have tabular data, there's an opportunity to generate a set of constraints and to verify against that during use. Let's see whether that has done it. It has. So here's an example verification just with some different data, and you see there are a set of failures. Some of them are unsurprising, the range of request dates, so it generates a constraint for date fields, which don't make very much sense. One of the new things is to generate relative date constraints instead, so not say what's the absolute range of dates, but how are they relative to today or relative to some reference date that you specify. So those have failed. You'll see the minimum and maximum values. There are some fantastic minimum and maximum values here. There's a minimum card fee of minus £4.9 million, which is the lowest credit card fee I've ever come across. The bad news is there are some quite high ticket prices as well. In fact, there's an 877. Well, you see the biggest one's a lot better than the negative smallest one. But the biggest total price is £20 million, so that's not very good either. But you get the idea. So moving on. Yeah, definitely moving on. So yes, you should be generating a set of constraints at every stage in your process if you possibly can, and verifying outputs just as much as inputs. So let's talk briefly about rexpy. You probably all know what regular expressions are, and you've probably all heard Jamie Zawinski's thing about some people, when confronted with a problem, think, I know, I'll use regular expressions now. Now they have two problems, as Jamie said 20 years ago. Regular expressions are ways of characterizing patterns in expressions. Again, I'm sure you all know this. I'm not going to belabor the point. And they're kind of our go-to way of characterizing strings. So if you have, not if you have free text strings, but if you have identifiers of various sorts, if you have national insurance numbers and telephone numbers and zip codes and IP addresses and stuff like that, it would be nice to make sure that the data conforms to whatever patterns there are. And if you've got good examples of those, in principle, we shouldn't have to write the regular expression ourselves. We should be able to get a machine to do that. And that's what rexpy does. It's in the TDDA library, though in the library at the moment it doesn't generate constraints. I'm not sure why we'll make it do that. So regular expressions, they have pros and cons. Well, they have a pro anyway, which is that they're powerful, and I suppose they're ubiquitous. But they're ugly, they're hard to write, they're even harder to read, they're even harder to debug, and they're pretty hard to escape as well. Though if you don't know about it, you should use raw strings in Python, because they're fantastic for regular expressions. They mean you don't need as many backslashes. So the idea is, why not let the computer do the work? Third demonstration, let's see if this one works. So there's an online version of this as well. But if we go to the right place, I have a file of postcodes somewhere. So here are some postcodes. Again, apologies if they are too small to read. These are UK postcodes. Apologies for the fact they're UK postcodes, which have a structure you can see. So as a trivial example, if you say rexpy on those, it will generate what you'll all recognize as exactly the right regular expression. I mean, it's a pretty easy one, but it's saying you get one or two capital letters, followed by one or two digits, followed by a space, followed by a digit, followed by two capital letters, which is exactly the standard pattern for, excluding London postcodes, admittedly, that's the standard pattern for postcodes. So that's what rexpy is about. It's an entirely heuristic thing. It's not even using a quality measure, let alone optimizing anything. It's very much specialized for identifiers and structured data, not for human sentences and stuff like that. And it really prefers ASCII to Unicode at the moment. I mean, it uses Unicode, but it really prefers the Unicode characters less than 127. But it's pretty fantastic. It won't always generate a single regular expression. It often generates a set. And though, in principle, we'd like it to get better at alternations and produce fewer regular expressions, in fact, the fact that it generates different ones for different kinds of strings quite often ends up being very useful, because it quite often turns out that it generates one that correctly characterizes all the good data, and like 30 that characterize each of the bad examples in your data. So although we'd like to make it smarter, the fact that it's stupid is actually quite helpful. So I'll finish by talking a little bit about what we've got planned for TDDA. The things that are already implemented, just to whip through them, and there are 3 columns here with ticks. So there's stuff that we've tried, stuff that is implemented in our software, and stuff that's already in the TDDA library. But everything ends up in the TDDA library. It's not that we're holding it back. So we have reference tests, we have type constraints, we have min and max constraints, and for strings, those turn into min and max length constraints. We specify sign separately as well, because even if you change the range of a numeric value, changing its sign is rather more significant, so we keep that as a separate constraint. We have nulls constraints, mostly saying that you can't have nulls if you can't or don't. Duplicates constraints, saying that you don't have duplicates if you don't, so looking for sort of key fields. We have categorical values constraints. We have these regular expressions constraints. And as I say, the code for generating the regular expressions is in the library. It's just not wired up to generate and check constraints yet. We have these time delta constraints I mentioned, so not just looking at the absolute range of dates, but the range of dates relative to when you run it or relative to some date that you specify. And we've also been experimenting. In our software, we have stuff comparing the sort of start date, end date type thing I was thinking about, saying this pair of fields have a satisfy a constraint. And we have foreign key constraints, checking that foreign keys between tables work in whatever way they're supposed to. Things that we're hoping to do, and this really is just about the end, very briefly, we want to combine 2 different TDDA files or automatically give you the ability, a bit like in the reference test, to say, OK, I've checked all the violations in all the failures in running this set of constraints against this data set, and they're all OK. So write me a new file that combines the old one and the new one. We can kind of do that, but not in the most sophisticated way. Conditional constraints, so if you fix your data, maybe there are constraints that ought to be true for data after a certain date, but obviously aren't true if you don't update the old data, or vice versa. We're interested in characterizing incidents and doing root cause analysis, actually doing some machine learning to figure out what's going wrong when constraints fail. All sorts of reporting could be improved. Apparently JSON's a thing, and we probably ought to do something with that and JSON schemas. And that'll probably pretty much do. Oh, God, there's more. Yeah, and all this stuff, too. Distribution shifts. Nearly constraints are really interesting. A constraint that isn't true, but it's very nearly true. So, the problem with that is it's like almost no one defaults. We'll just say no one defaults. That wouldn't be a good example of this. But a good example would be 4 out of your million records, have got strings when everything else is actually an integer or whatever. Constraints editor would be nice. Constraint severity levels, alerting, all sorts of stuff. I'm running out of time. So remember your ABC. Always be checking. Go away and do test-driven data analysis. And you can pick up all the stuff. Well, that's me. You can get in touch. There's a blog at TDDA Info. The code is at GitHub. There's a Slack channel. If you mail or tweet at me or us, we'll do that. There's a Twitter account. Be careful. Those are zeros on the end of the Twitter handles, not zeros. That would be an error of interpretation. Thank you for your time. I'd be very happy to take any questions if I haven't talked too long.
So be quick. Any questions?
Besides the stuff about regular expressions, in what way or how can TDDA help me if I'm already using PyTest?
If you're already... So I'll avoid the cheap shot of saying nothing can help you if you're using PyTest. The TDDA library works with PyTest as well as unit test. It's fully tested. The constraint stuff works. So yeah, I don't know if I'm misunderstanding your question, but there's nothing to stop you using all this stuff. And indeed, it's tested with PyTest as well as unit test. I suspect you meant something different. Okay.
Nice talk.
Thank you.
When you talked about reference testing and you were like updating or capturing the output of the now updated tests,
yeah.
I would do that locally because then only I know that I fixed that problem or that's the known problem. Do it on the continuous integration server, then it has to happen automatic. Like it's just a question of orchestration. How do you manage that?
Yeah, I mean, the way that we do that is we keep the reference tests in Git, and so you update your checked out copy and then you push it to the server.
In the same repository?
Yeah.
Okay.
But we're not trying to solve I mean, there doesn't seem any point in building another distributed version control system because we're not as clever as Linus.
So one last question, time-wise, at least now here by microphone.
It looks pretty cool. One question I wonder is like, for this testing, you need a perfectly valid data set, right, in the beginning. So it has to be cleaned and maintained. And how do you make sure so that's like a lot of manual work you have to put in first, right?
Yeah. So ideally, you would have completely clean data to generate your constraints from, and ideally, you'd check your constraints when you generated them. But in practice, what you find is more often you just generate the constraints, and if you can't be bothered to look at them or there are problems, you just put them in place. Stuff breaks the next time you run it, inevitably. Some stuff should break, right, because it puts a maximum number in, and that number was just a feature of your data set, and it shouldn't have had a maximum at all, or it should have been much bigger. And that's fine, but if you then update your constraints file over time, those things get better. The danger is that you always make everything looser doing that rather than making it tighter. The other thing is, a bit like any set of tests, what you have to do is, from time to time, you will spot things that are wrong, and you have to go back and reflect those in your constraints. What you can do that helps is you can be relatively conservative about what data you use to generate the constraints. So you can hand check 10 records or 100 records or whatever, and in many cases you can still generate a pretty useful set of constraints from that. The other thing you can do is you can generate constraints at you can generate constraints every time and see how they're changing. In fact, a diff tool for that is another thing that would be really nice to have. Hopefully that helps a bit. Thanks.